Hello, welcome to numerical ship and offshore hydrodynamics. So, today we are going to discuss this following topic, that formulation of the source panel method. Now, if you remember in the last class I said there are three different kind of panel method based on the discretization. One is source dipole that we have solved for the infinite fluid domain, and then the source panel method, another one is a dipole panel. Let us see that what the other methods are here. And this is the keyword that you have to use to get this lecture. Okay. So, let us go back to this. Now, formulation of the integral equation, there is a three type of integral equation that we can think of. One is the source dipole distribution over the boundary surface, and that we have already discussed in when we solve the infinite domain fluid problem and get the infinite frequency added mass. That time we have discussed this, and now today we are going to discuss what is the only source distribution over the boundary surface and what is the only dipole distribution over the boundary surface. Okay. So, now this is the typical source dipole distribution, and we know very well what is this equation, right. Here you have this left hand side, this alpha p. If you remember, this alpha p is nothing but 4 pi inside the fluid domain, right, and then 2 pi minus 4 pi inside the fluid domain, minus 2 pi on the boundary and 0 outside the boundary. Sometimes people actually take this alpha p, the value is 0, half and 1 based on that position is outside on the body, or it is the inside the domain. Okay. So, you can take alpha p 4 pi, 2 pi, 0, or you can take 1, half and 0. Anyway, now inside this, now let us consider that if there is a point here inside the boundary. Okay. So, then this is the equation. So, where phi is the here inside the integral equation, this phi is distribution of the velocity potential on the body, and then in the left hand side this phi indicate the velocity potential anywhere in the fluid domain, right, and then this is the equation, and you can call this a source dipole distribution. Now, think of a hypothetical situation. So, what is that hypothetical situation? Like, in order to place this arbitrary point inside the fluid domain, let us place inside the body. Now, inside the body there is no fluid, right. So, it you can think of there is a imaginary domain. Now, if you write the same integral equation for this imaginary domain, okay, so then actually we can write this equation as follows. Now, here what I said that this p, now inside that if I go back here, this p is now inside this b. Okay. Now, if this p inside this the b, then this is, let us assume that this is the boundary integral equation. Now, here one must note that the normal is definitely the opposite. Now, see, always we take a convention that normal should be the inward to the fluid. Now, if you look at this the previous this one here, this normal, now you can see it is along this p here in this direction, this is the inward to the fluid. Now, if you take inward to the domain, better to say. Now, if it is here inside the middle of the b, okay, somewhere here, so then the normal should be the inward to this. So, definitely the direction is normal should be opposite. You have to understand this very well. That is why I said here definitely you can see the phi dash n is nothing but minus of phi bar dash n, it should be n dash should be equal to minus of n. So now, that is why when you call this as n dash, remember this n dash, it should be the inward to the body B, right. Like in case of the previous one, it should be the inward to the fluid. Now, here it is inward to the body, that is the positive direction of the normal. So, therefore, I understand very well that n dash equal to minus of n, right. So, with this understanding, now if you look at this equation 13, it is the same equation. Instead of alpha, I can call it alpha dash, okay, and instead of phi, I call this as a phi bar, and phi is because it is the same phi, right. So, now, if we look at my equation 12, this one, and then if I take this equation 13, this one, and from these two equation actually I can get the equation 15. It is simply by adding the equation 12 and equation 13. Why? Because alpha dash p, now it is the outside the domain. So, the value is should be equal to 0, because the hypothetical domain. So, therefore, the value should be equal to 0. So, now if we add this 12 and 13, then definitely we are going to get this equation, right. Now, what to do with this equation? So, here it says phi p equal to over the S, it is phi n minus phi bar n into G minus phi bar into G n into d s, right. Now, from this equation, how we can obtain the source panel method or the dipole panel method. So, now, if I look at this equation 15 and if we apply the Dirichlet boundary condition, so it says that at the boundary that phi bar equal to phi, because it is a hypothetical boundary, that second one, that based on that actually I am getting this equation 13, that equation is a hypothetical boundary. So, I can take at boundary any value for this phi bar. So, I said that if I take phi equal to phi bar, and then if I take del phi, I mean this is the second one, that phi minus phi n minus phi n bar, if I take as sigma. Now, what I did is, here I use the Dirichlet boundary condition. I said that I am taking phi equal to phi bar. So, this part goes to 0, right. If I do that, then actually, and I am writing that phi n minus phi n bar equal to sigma. So, if I do that, then I can get the equation 16, right. Now, if I do the opposite, now if I use the Neumann boundary condition, and if I write that phi n equal to phi n bar and phi minus phi bar equal to mu. So, then I can get the equation 17. So, this equation 16 is the source panel method. I mean, this is the boundary integral for the source distribution, and then equation 17 we can call this the integral equation. It is the distribution of the dipole. Why? Because if you look at this equation 16, it is the distribution where the G is only there, right. Only the source is there, but dipole is absent, and in equation 17 the only dipole, that G n is there, but the source is absent, right. So, that is why we called this the only source distribution method, where we have the I mean there we have only the G, but we do not have the G n. Now, taking this only source distribution, how do I solve this equation? Now, here if you look at this equation, now here you can see there is a 2 unknown, right. Now, let us go back to a little bit in the, let us go back to our board work. If you remember that in our source dipole distribution, this is nothing but, let us take alpha p, of course, alpha p phi p equal to, here you have over this body S, and then we can call is let us take phi del g del n minus then g into del phi del n into ds, right. Now, if you do that, then here if you look at this equation, everything is known to you apart from this phi, because del phi del is nothing but your V n, that is known to you, and then g is also known to you, and then del g del n also known to you. So, only thing that is unknown to you is nothing but the phi. Now, if you look at this equation, here you can see that you have actually two unknown. One is that phi, of course, this is what I am going to obtain, and second one is the sigma, the strength of the source, right. So, but then we need two equation, right. So, what I do is we differentiate that equation 18 with respect to n. So, if I do this, then in the right hand side we have the del phi del n, which is nothing but my V n, the boundary condition. If I apply over here, it is V n, and then if you integrate this, we will get this expression. Now, here this equation 19, it is strictly for the lower order panel method. However, in the higher order panel method, you really do not have this, the term half of sigma k p. So, now how this equation is coming, let us try to see. Okay. Now, in this equation, what I am getting right now is phi p is equals to integration into sigma into g into ds. So, this is I call, this is the only source distribution. Now, if you discretize, okay, I just missed the alpha p, sorry. So, if you discretize this one, so in lower order panel method, what you are getting is alpha p into phi p, and that should be equal to, now if I do the summation. So, you can take summation j is equal to 1 to number of panel n, then it is phi j, and if you remember, it is d into I into j into ds. Now, here what I am doing in each panel I am doing it. Let us say take the constant panel method, and it will take the if you take the what you call that 1 point Gauss quadrilateral. Normally, we do not do here, but for the understanding this, the second equation, let us try to do that. Now, if you differentiate with respect to n, then what you get? You get alpha p multiply by the I mean it is del phi del n, of course, and then it is sigma j equal to 1 to n, then it is sigma j into del g del n I comma j into ds. Okay. So, now alpha p is there. Now, if I replace this as phi I, if you remember correctly the last time when you solved this, if you take I, then here I have the summation j equal to 1 to n, and then we have sigma j into del g del n into I into j into d of s j, let us say. Now, here if I take I equal to j, okay, then I know this integral of this value is become 2 pi. Now, if I break it I equal to j and I divided by alpha p the whole thing, okay. So, then what you get as follows, when I is equal to j, then I have here it is 1 upon 4 pi, and then I have the sigma I and multiply by the 2 pi, right. plus of course 1 upon alpha p is there, we can take it is 1 upon alpha p into summation j equal to 1 to n into del g del n I j into d s I j. Now, if you take alpha p inside this Green's function, so here I can write is half of sigma I, because this will cancelled out, and then I just write this same as the integral from s into, we can write here at okay, sigma is here, right, sigma j is here. So, it is sigma j into del g del n into d s j. Now, you see that is why this half of sigma I is coming. Now, it is only happening when you have this lower order parallel method, right, fine. So, now, so this is now I understand the equation 19 correctly, right. This is how this equation 18 and 19 should be. Now, I solve this equation 18, right. I mean, so first you need to solve the equation 19, right, because in equation 19 now all the parameters is now known to you. You know the right hand side is nothing but your the body boundary condition, right, that you know. You know the Green's function del g del n, and also so this is some, that is the only thing that you I mean sigma that you need to know. So, here the only unknown is nothing but your the sigma, right. So, therefore, first we solve this equation 19, I get the expression for sigma, and then that expression I substitute in the equation 18, and then I get the value for phi. Okay. So, now this is how actually we can discretize the surface. Now, as I said that in higher order panel method, this is how we discretize the surface. The patches are big and we really do not assume that phi to be constant, and in that case remember in this equation 19 you do not have this half into sigma that you do not have, right. Now, in here in lower order panel method is a fine discretization we do, we assume everything is a quadrilateral panel, and then we can solve this problem, solve the thing, and here in that case you have to take this as half sigma I, right. So, this is how, I mean again I am repeating the same thing again and again, just so that you will be more comfortable with these things. I understand that it is in order to understand it fully, repeatedly you have to see the thing. So, again many times I said the same thing, here also the idea is discretize the body, that boundary, this small quadrilateral patch or triangular patch or both quadrilateral or triangular, and after that we have to assume this velocity potential to be constant for a single panel, and it should be the different for the different panel, right. So, once we do that, then we can solve the equation. Now, here there is some understanding of the what I said. Now, I just take a one quadrant of the this sphere. Now, here sometimes we are using the symmetric property. Now, this is a geometrical symmetry in all other axes, right. So, I think we will going to discuss later on, like if we model if that body has a symmetricity, then you do not need to model the whole thing. So, you can model the one part of it, and then you can use the property of the symmetric property, and you can get the all other things anyways. So, in case of a sphere only 1/4 is good enough for modeling. Now, if I do that, now the idea is to tell you that here you can see this phi 1, like it is may not be visible properly. I just write phi 1 this panel, phi 2 next panel, and phi 3 some panel is very away from this first two panel, and you can see the phi 4 is further away. So, here unlike the finite element where you need this matrix in a specific format, here we really do not need that way. Okay. And if you remember, the finite element is a diagonally dominant matrix, but here is a this matrix sparse matrix. I mean, that means it has the value everywhere, right. It is not diagonally dominant. Okay. So, therefore, here it is not essential that you take all the panel in sequential order or some order, not necessarily. Okay. So, this is that actually makes your life little bit easier. Why? Because I will tell you that when you model it or you mesh it using some commercial software, sometimes it maintain, sometimes it may not maintain this orientation. So, absolutely there is no problem with this. Okay. And also again the same thing, that the panel you need to avoid, right. So, these are the panel that extremely bad aspect ratios panel you need to avoid, or also you need to avoid that this angle is very high, right. So, it is a thumb rule. I do not say this is the some theory associated with this, it is not, of course, but when you using some software like Wamit or Moses, some other software. So, that time you need to take care that your this aspect ratio, I mean you will get the better result if this aspect ratios, if you maintain 0.4 to 1, and for the and also for the quadrilateral panel, this angle should be between 70 to 135 degree. I mean, if you maintain this, then definitely this yeah, that what is said, that quality of the result would be good. Like it is very tough to tell that there is a many dependencies, like this numerical code, writing numerical code never be an easy task, because it is not all about the theory, it is all about that numerical. I mean, sometimes everything is correct, but you really do not understand why it is not numerically stable. So, there will be many reasons. So, you have to make sure that everywhere that you are at least you are following the basic thumb rule, so that that the core engine, which is the writing the integral part, right. So, that does not take taken care of other thing, like the normal is define, the normal is fine, and then this area is not very thin, aspect ratio is not that bad. So, that variation, that you are what you are assuming that phi is constant for a one panel, different for the different panel. Now, if this two panel is very large, so you can see that I will tell you that what I mean, like so now if the aspect ratio is bad, then you can assume that that now this is the two thing. Let us take these are your panels. Now, here you have this, let us say phi 1, let us say phi 2, then phi 3, and you have phi 4. Now, you see that phi 1 and phi 3 is very close by. However, phi 1 phi 2 is far away because of your elongated panel. Now, compared to that, if you have this panel, right, some panel like this, and then you can see that the distance from this and distance from this, I mean this neighboring distances are in kind of almost like a same order, like this sort of things helps actually in your coding. So, that is why you need to take care about all these things, right, to do that. Okay. So, I think today we are going to stop here at this point, and then we are going to set up the integral, I mean the conversion of the integral equation to the algebraic equation, how actually do with respect to this lower order panel method. Now, here it is not as same as before, I am not taking that 1 point Gauss quadrature rule. We have to take either 2 point Gauss quadrature rule or 3 point Gauss quadrature rule, right, and what is that, and then how I take care about the normals in very unified way, and how I do the perform the integration over the panel. All such thing will be discussed in the future classes. Why I am discussing all such thing, that is one major reason is this computation of this Green's function. Okay. Now, here we definitely are going to discuss later on here that just to realize you that how complex things are here. Here you can see there is a two component, one is 1 by r plus 1 by r dash, so that is we can call the Rankine, and when this I and j is very close to each other, that time finding out this Green's function, this Rankine part is very difficult. Now, this is one part, forget about this. Now, let us take the other part of it, which is the regular part we can call. Then you can see here we can have in this equation. Now, you can see the integration is 0 to infinity. So, that means you understand that if you look in the summation form, so at that point that summation should be infinity. So, we have to go look for a the convergence solution, right. That means, your numerical solution should be convergent, right. And then top of that, so now the integration limit is infinity, top of that you have this all this Bessel function, this first kind, second kind, modified Bessel function, and all of these functions are also in infinite series, as you know. So, now you can see the complexity of this particular thing. First of all, it is not only that it is as a singularity where I equal to j at that particular point, also you have to formulate you need to compute a Green's function, which the integration limit it is 0 to infinity, right. So, therefore, it must be convergent. I mean, you have to find look for the convergence, right. So, that is how that sometimes you can say that this result is not coming correctly, you can find out some numerical inconsistent result is coming. Why it is so? Because sometimes when you integrate this, not necessarily that you are if you are not writing very tight code, okay, and like if you take care of all aspect of the meshing everything, then this might go infinity. So, then at that point you do not get the convergent solution. So, therefore, that is why that is the main reason I am keep telling that that thing that you can actually these things is not in your hand, is the coding the convergent non convergent does depend on then what is your source point, what is your field point, how are doing the integration, many things, and it is not possible for us to look at each aspect going through the code and make sure that things are going well. However, what we can control from the very beginning, that the basic things, the basic geometry parameters, if I set it correctly, like the meshing, the normal should be uniform, it should be the outward drawn normal or inward drawn normal. Based on that, you have to write the code, you have to adjust the sign, minus, plus, everything. If these things if you do correctly, definitely that there is a possibility that you will get the better results at the end. Okay. So, I think today let us stop at this point, and in the next class we are going to form the algebraic equation. That means, that we have this integral equation, and then this integral equation we are going to transfer into the algebraic equations, and then we have to see that where we have the challenges, and then how numerically we sort out those challenges, and finally, how I get this added mass, damping, exciting force, etc. Okay, we are going to discuss from the next class. Okay. Till this point, thank you.